Okay, so this is the last type of cycle you will see in Thermodynamics 1, ENGR 251. This is called Otto cycle. Before we do this type of question, let me summarize the differences of all those cycles we've learned in this course. First of all, we have Rankine cycle. In Rankine cycle, you don't have ideal gas. You have liquid water and steam, superheated steam. So we're going to use property tables to find the values of enthalpy, pressure, temperature, blah, blah, blah. You'll see Rankine cycle in, I don't know, nuclear power plant. And then for Brighton cycle, which uses ideal gas, so you can use ideal gas law, PV equals MRT. You can use isentropic relationship equations. You can also replace your delta H by Cp delta T, because the prerequisite of using this and that is just you're going to have ideal gas law. Otto cycle is another cycle that uses ideal gas. Where do you see Otto cycle? You'll see it in your car. If you have a car, you have Otto cycle. It is found in the internal combustion chamber. Okay, so the compression ratio of an ideal Otto cycle is 8. At the onset of the compression stroke, the pressure is 0.1 megapascal and the temperature is 15 degrees. Let's draw this out. This is the cylinder, this is my piston, and currently it is at the bottom, called the bottom dead point. It's going to move up. In this process, we're going to supply work int. State 2, we have the same cylinder, whereas the piston is already in the on the top, on the what's it called, top dead center. State 3, the piston is still up, but we're gonna give it fire. This is where the ignition happens. So we got Q in. And the last one, the piston moves downward, generating work out. And you got heat out. Let's label something here. We got volume 1, volume 2, R is equal to volume 1 divided by volume 2. R is compression ratio, and that's given. That's 8. That means my V1 is 8 times greater than V2. From state 1 to state 2, it's isentropic, meaning adiabatic. Reversible means ideal. From 2 to 3, it's isochoric, meaning my volume doesn't change. As you can see, the piston stays up. From state 2 to state 3, volume doesn't change. This happens like in a split second, real quick. So state 3 to state 4, another isentropic process. And don't forget 4 to 1 is our isochoric again. Volume doesn't change. This is V2, V1. V2 means small volume, V1 means big volume. Now we can start solving this problem. Again, we can use isentropic relationships. We can use ideal gas law because we're dealing with ideal gas. State 1, let's see what we have. Compression ratio is 8. So P1 is 0.1 megapascal. And T1 is 15 degrees C. Heat supplied to air per cycle, that's Qn. So let's label here. Let's label it Q in, that's equal to 1800 kilojoule per kilogram. Okay. So state 1, we just have temperature and pressure, and that's enough. Don't forget to convert degrees Celsius into Kelvin, because we're going to use Kelvin values in the equations. Now, I'm not too sure if this step is necessary, but let's just write it down. Since this is ideal gas, PV equals RT. So my V1, the reason why I write this down is because I have temperature, I have a pressure. So automatically I can calculate V1. May be necessary, may not be necessary, I don't know. But let's just do it. P1 is 100. That gives me this. We also know the compression ratio. Compression ratio, pay attention, is not a pressure ratio, it's the volume ratio. So it's not P1 over P2. It's actually V1 over V2, that's 8. Say 2. We got V2, that's 1/8 times V1. That gives me now, since state 1 to state 2 is isentropic process, we can use isentropic relationships. This is found in the equation sheet. And our P2 is going to be P1 times V1 over V2 K. Here, you don't have to write down the values for V. You can just use compression ratio, because V1 over V2, yes, you can write down this divided by that, but it's not necessary. It's just pressure ratio, compression ratio, sorry. And that is 8. K is 1.4 for air. That gives me this much. You see that P2 is a lot higher than P1, because state 2, we are compressing air. We got smaller volume. Naturally, you're going to have a very big pressure. That makes sense. We're going to use the isentropic relationship for T2. And we can only use this because ideal gas. The formula for temperature is this. K minus 1 instead of K. So my T2 is here. You can write this is just R to power of K. This is just R to power of K, or just leave it like that. But you know that's R. My temperature T1 is 288, compression ratio 8. K, it's K minus 1. So that's 0.4. And T2, I have this. Is it normal that T2 is greater than T1? Well, yeah, you compress air, you're going to expect a higher value for temperature too. How about work in? Because like I said, from state 1 to state 2, we're going to supply a bit of work. So work in. What is that? Again, we're going to apply the first law of thermodynamics for closed system, not open system. We can use that in Brayton cycle and Rankine cycle, but here, since we have a closed system. Why closed system? Because we got a piston side in the device. We're gonna treat it as closed system, but in real life it is not, because we got exhaust what's it called, the valve's gonna open, there's mass entering the boundary, but here we're gonna just treat it as a closed system. So instead of H, it's actually U. Remember, U is for closed system and H, enthalpy, is for open system. There's no heat. And once you see U and once you have ideal gas, we can replace it by CV, not CP. CP is for H, and H is for open system. CV, delta T, is for internal energy. Internal, so enclosed. So that's a closed system. We got negative 268. It's normal that it is negative because we are supplying work to compress, right? Remember this? When you compress something, you're gonna need to do work for it. So that's why it's negative. It's work in. Now let's do stage 3. Stage 3, what we have is volume that remains the same as V2. So we can say V3 same as V2. And Qin, that's given. We have 1800. So we can calculate T3 using heat. We don't use the isentropic relationship to calculate T3 here because from 2 to 3, it's isochoric. It's not isentropic. So ideal gas, it is ideal gas, but we cannot use it. So the second solution to calculate T3 is through, well, pretty much the same formula here. It doesn't do work because volume remains the same. No volume, no work. And since this is ideal gas, we can replace it by CV delta T. Well, Q is given, that's 1800. CV is given. Well, it's not given, but it can be found from the property table. T3, that's what we're looking for, minus T2, which is calculated out. So T3 is this, which is pretty hot, right? We got ignition here, so we are expecting very high value for temperature here. How about P3? Well, guess what? We're gonna use the ideal gas law. PV equals MRT. Since there's no M, we're gonna use P small v is equal to RT. We just have T3, so our P3 is gonna be R T3 divided by our V3. What is our V3? V3 is the same as V2. So we're gonna have very big value for pressure. Because we have extreme condition here. Ignition, when you see ignition, that means high pressure, high temperature. So that's done for state 3. Let's move on to state 4. We have V4, that's the same as V1, the big volume. And then since state 4 to state 1, we got what am I doing here? Oh, it is isochoric. Yeah, it is isochoric. Isentropic compression, isochoric, heat addition, it's 3 to 4. Sorry, it's 3 to 4, not 4 to 1. So state 4, we can use, since this is isentropic, we're talking about from state 3 to state 4, isentropic process, we're going to use isentropic relationships. So we have P4 over P3. What is V3 over V4? V3 is the small volume, V4 is the big volume, so it's the inverse of the compression ratio, 1 over 8. And that gives me, we can use this because this is isentropic process. How about temperature 4? Again, this is the small volume divided by big volume, so it's going to be the inverse of compression ratio. How about workout? Since we got temperature and pressure, we got everything for state 4, we can calculate workout. This is U, not H, because we're dealing with a closed system. No heat, because it is adiabatic, it only does work. We're going to replace delta U by CV, delta T. We can do this because, again, this is ideal gas. And that gives me this much. Once we got work out, we can calculate work net, which is equal to work out minus work in. And that is 1, 2. Pay attention, this is an absolute value. And the thermal efficiency of the system is work net divided by Q in. And that's around 56%. Double check with Cardinal. Low temperature divided by high temperature. Where's low temperature? Low temperature is state 1, 15 degrees Celsius. Convert that into Kelvin. And our high temperature is at T3. Pay attention, don't use heat, it's temperature. It's not 1800. And that gives me 91%, which is crazy. In real life, even 56% for an internal combustion engine, it's pretty much impossible. It's still very high, but everything here is theoretical. So as long as your calculated efficiency is lower than Carnot, that's good.